Good evening, everyone. So we'll be discussing about the contents from week 11. So in week 11, the video start with the uh, linear regression, how the linear regression is constructed. So in case of linear regression, we had a model of the form y is equal to w transpose phi of x, where phi of x represents a basis function. Now, what all this would include is it could be any row input, which can be x, or it can be polynomial terms, such as x square, x cube, etc. So, this was the linear regression setup. And here, when we are given a training set, which has the form xi, yi, where I is from 1 to m is the number of samples. What our goal in linear regression was to find the weight vector W that best explains this data. So in week 11, the video starts with linear regression, where in linear regression we have a model y which is equal to w transpose phi of x, where phi of x is the basis function which can include row input or any polynomial terms. If x is the input, it can be x, x square, x cube, etc. And we have a training data set xi, yi, and each of the I correspond to the number of samples, which is n. So in linear regression, what we were doing was we find the weight vector W that will best explain this data set xi, yi. So if we assume that the data points are identically and independently distributed, the probability of observing the entire data set is the product of individual probability. So this is what we call as the likelihood function. So this means the probability of observing the entire data set is the product of probability of individual sample or individual probability. So this is the likelihood function which is given as P of y given x comma w. X is the input, y is the output, w is the weight vector. So this is the product over all the samples I, the individual probability which is given by P of yi given xi comma w. Then if we model each observation, that is each of this observation as a Gaussian noise around the model prediction, that is if this is the model prediction yi, and if we model this each of the observation as a Gaussian noise, then this is represented as W transpose phi of xi comma sigma square. Then the individual probability can be written in this way. So this would be P of yi given xi comma w is equal to n of yi given w transpose phi of xi sigma square. Then this we can express as 1 by square root of 2 pi sigma square e raised to minus yi minus w transpose phi of xi the whole square divided by 2 sigma square. Now, when we take the negative log of the full likelihood, this will actually, when you substitute and do it, that is minus log of p of y given x comma w, this part. When we take the negative log of the likelihood, this will be proportional to the yi minus w transpose phi of xi the whole square. That is, this is the mean square error. So minimizing the minimizing the maximum. So minimizing this mean square error is equal to maximizing the or it is a maximum likelihood estimation under the Gaussian noise model. Now the problem with maximum likelihood estimation is, as we increase the degree of the polynomial, the weights will become extremely large in magnitude. So this will force the model through very noisy training point and will lead to overfitting. So as the degree of polynomial increases, there are chances of overfitting. So very large magnitude of W values will indicate that the model is not actually learning anything, but it is overfitting. It is learning the noise rather than the signal. So now coming to the Bayes. So using the Bayes rule, we can write the posterior distribution over the weights given the training data. So the posterior is given by P of W given y comma x. We can write this by using Bayes. W divided by P of y given x. So this term, if you see, this does not depend on W. It is a constant normalizer. So we can remove that term and we can write that P of y given W comma x. This is proportional to P of y given x comma W into P of W. So the term P of W, this is called as the prior distribution. That is, this is our belief about W. This is our belief about W before seeing any data. So before seeing any data, we believe that this is the value of W. So to discourage very large weight value, we usually choose a Gaussian prior with zero mean. Now, so this is the prior. So this is what we usually start with. Then, when we take the negative likelihood of the posterior distribution and using a Gaussian likelihood, so this is our likelihood This is our prior and this is our posterior. So when we take the negative log of the posterior, and when we use a Gaussian likelihood and a Gaussian prior, we get that the minus log of P of W given y comma x, this is proportional to sigma over I yi minus W transpose phi of xi. This we found before. This is the mean square error. Then plus 1 by 2 alpha square norm of W square. So this we get. So when we take this as a Gaussian prior, we can find that this P of W will be a normal distribution with W given 0. Sigma square I. So this is 1 by Z minus e raised to minus of divided by 2 alpha square, and this alpha value is something that we can tool. Okay. So this prior we can replace as 1 by 2 alpha square. Now for so here this becomes this when large values of W exist, the probability drops off exponentially, and it will become this 1 by 2 alpha square W norm of W square. So then we can write here lambda is equal to 1 by 2 alpha square. Then we get that this L map of, that is the maximum a posteriori, is MSE. This is the mean square error loss plus lambda times norm of W square. That is, so you have to minimize this. Then when we minimize this, we get W is the minimum of the argument of sigma over I yi minus W transpose phi of xi the whole square plus lambda times norm of W square. So this is called as ridge regression. So this is the way of regularization. It will help with overfitting. Similarly, if instead of the Gaussian prior, if we use a Laplace prior, Laplacian prior, that is, this P of W value is proportional to the exponent of minus of W by V. Then this will give the L1 norm. L1 norm is just the absolute value. It's the sum of the absolute value. So then this will become the MSE loss plus W. So when the weights become very large, there are two ways to deal with overfitting. One is this ridge regression, where we take the norm square, and the second one is the lasso regression, where we take the one norm, the L1 norm, which is norm of W. So this is the L1 regularization. Now coming to, so when both the likelihood and the prior are Gaussian, the posterior will also become Gaussian. So this can be written as P of W given y comma x if n of W given where this is the posterior covariance and mean. So the posterior covariance, it will tell us how uncertain we are about the W value. When there is a small Sn value, then that means the data has like it has reduced or it pinned down the weights more tightly. Now, in Bayesian regression, we want the predictive distribution over the output y star for a new input x star. So instead of a point estimate, what we want to find in Bayesian regression is P of y star given x star x comma y is the integral over P of y star given x star comma w into P of w given x comma y dw. So the integral will average the prediction over all the plausible weight vectors weighted by the posterior. So for Gaussian likelihood and prior, this integral is analytically it is tractable. So P of y star given x star x comma y is equal to n of y star given mu star sigma star square. So the predictive mean will be then W transpose phi of x star and the variance is sigma square plus phi of x star square. So the first term, this is the observation noise, and the second term is the uh, as the W grows like so this is what when x star is when the new input x star when it is far from the training data. This will tell us about the uncertainty of the model. Okay. So, so the maximum likelihood it is equal to the mean squared error, and then the in Bayesian prediction instead of a point estimate, we are trying to take the predictive mean and variance. We try to calculate that by taking this integral. One question from previous year assuming this: when a Gaussian prior is used in maximum a posteriori estimation, what type of regularization does it correspond to? L1 regularization, L2 regularization, elastic net regularization, dropout regularization. So L1 regularization is used when the prior is Laplacian. When we have a Laplace prior, then we use the L1 regularization. And when the prior is Gaussian, then we use L2 regularization. So the question is, when a Gaussian prior is used in MAP estimation, what type of regularization does it correspond to? So when a Gaussian prior is used in MAP estimation, it corresponds to L2 regularization. So, the L2 regularization. What is the key difference between Bayesian regression and MAP estimation? Bayesian regression uses a different cost function. MAP only uses normal distribution. Bayesian regression provides a predictive distribution rather than a point estimate. MAP doesn't require gradient descent. So Bayesian regression provides a predictive distribution rather than a point estimate. So MAP estimation, it will find the single most probable value for model parameters given certain data and prior distribution. But so it will essentially provide a point estimate that maximizes the posterior probability. But Bayesian will give an entire posterior distribution of parameters and it uses the complete distribution to make prediction. So it will result in a predictive distribution rather than a single value. So this is what helps Bayesian regression to naturally quantify uncertainty in its prediction. So distinguishing MLE from MAP in terms of their objective and overfitting behavior. MLE includes a prior term while MAP does not. MAP overfits small on small data set. Both are identical. MLE maximizes only the likelihood with no weight constraint. MAP adds the prior penalty, reducing the overfitting. MLE requires gradient descent while MAP can be analytically solved. Yeah, so MLE is argmax of P of the distribution given the parameters and does not have any constraints on the weight. And it can be prone to large weights and also overfitting, whereas MAP it acts as the prior acts as a regularization as we have seen before, like the L1, L2 regularization factors can be added to the prior. So penalizing large weights and also reducing the overfitting. So the answer is C. Coming to the next topic, which is generative model. So so far we were dealing with discriminative models where we learn the conditional probability, that is if y is the label and x is the data, then we were learning phi of y given x. So this is that conditional probability. So this is what was happening with the discriminative model. Now, when it comes to generative models, what was happening, what happens in generative model is instead of learning the conditional probability, it will learn the joint distribution. That is, it will learn P of x comma y, the joint distribution, which can be written as probability of x given y into probability of y, the probability of x in an unsupervised way. So this is via the Bayes rule. So a generative model that knows this probability of x comma y, that is the joint distribution, can recover. So from this we can recover what is P of y given x. First, this is P of x given y into P of y by P of x. So we can get this from here. So gradually, if we know the joint distribution, then we can learn what is this conditional probability. So the another important point with generative model is that we can sample new x values from the learned distribution, enabling synthesis of new data. That is, if we learn this joint distribution well, then we can create new data. That is, we can create new samples. So these are the two uses of generative model. One is if we learn the joint distribution, we can create new samples or we can create or synthesize more data. Another thing is if we know the joint distribution, then we can learn the conditional probability. So if we have, say, n training examples, x1, x2, etc. to xn, So this is drawn from some unknown distribution. We don't know how this data is generated. It is made from some random distribution. Now, this distribution is, say, p data of x. We don't know this p data of x. But what we do is we fit a model with parameters theta that will explain this data, that will explain the distribution of this data points x. So let this be p of x and some parameter theta. So this is our model, p model of x comma theta, and this is our data and the actual distribution of our data. We don't know what this is. Now, what we want is we want our the model that we are going to fetch to learn the distribution of the data to be very close to the actual distribution that was used to generate this data. So once we have a good model, then we can compute the probability of any sample. We can detect anomalies in the sample, and also we can create new samples. Okay. So once we know this model, or once we have a good model that generate the data well, then we can do many things, right? One is we can compute probability of new sample. We can generate new sample. Another one is we can detect anomalies. So what we mean by detecting anomalies is, suppose you have a data set with suppose you have a data set which contains MRI images, and the MRI images that you have are all normal MRI. Okay, so from this available data of normal MRI images, you can learn how a normal MRI would look like. And once somebody with some abnormality in the MRI comes, then because our model has learned how a normal thing would look like, it will detect that this is not something normal. So this is an anomaly. So it can be used that way if we can learn the distribution of the data from which the distribution from which the data is generated. So this is what a generative model would do, that it will learn the joint distribution x comma y such that it has multiple applications or uses than a discriminative model. Now, there are different types of generative models. That is, one is this autoregressive model. So they will factorize the joint distribution using chain rule. That is, if x is the data set, so probability of x will be given by probability of x1 into probability of x2 given x1, probability of x3 given x1, x2. These are all samples, x1, x2, x3, etc. up to xn, into etc. up to probability of xn given x1, x1, comma, x2, comma, x3, etc. up to xn minus 1. So this is what an autoregressive model would do, that it will factorize the joint distribution. And from this, it will learn how the how the distribution looks like. Now, the second type is this variational autoencoder. So, in variational autoencoder, you maximize the log of P of x. So, there is something called as evidence lower bound. So, we will come across this later. So, this is what a variational autoencoder will do. So that is, it will find I think so I'll first start explaining what is an autoencoder and then how it differs from a variational autoencoder. So when you come to that, we'll explain this. The third one is GAN. So they actually don't model the probability directly, but then uh, we can we have this model P of model that generate or that create or optimizes the distribution from which the data is generated. So once we have a good model that have learned the distribution well, then we can sample data directly from this model that is learned. So this is the one of the use of GAN. So starting with I can start with the autoencoder before GAN. So this is one of the generative model, or it's not actually a generative model, but then what happens inside an autoencoder? It's one of the unsupervised learning method. So why maybe autoencoder was used was, suppose if I have a very high dimensional data set. Suppose if I have say 200 features and I have many millions of rows of samples. But this maybe I imagine that there are 2000 features. But we know that all of this 2000 features may not be relevant for us. We don't need all of this 2000 features. So we can reduce the number of features uh, to something like maybe 100. Okay. So one way to do this is something that we discussed in last class. Do you remember? Dimensionality reduction. When you have a large number of features, you want to reduce it to a small number. Then we use one technique. So this is the PCA. So when you have a large number of features and you want to reduce it to 100, another way than PCA is to use autoencoder. Because what happens in an autoencoder is you have so autoencoder. If I take say an image of a cat, okay, imagine this is a cat. What happens in an autoencoder is it's just so this is an image of a cat, and what happens is an autoencoder has many layers. So this layers here will do some convolutional operation, some downsampling operation, like pooling, some activation function like ReLU, etc. And it keep on. So suppose if I have an image of size 128 by 128, it will keep on reducing this to a very small representation. Let this be say 10. Okay. Now from this 10, it will upsample and again do convolution and all those operations to reach back to the image of cat. So then the difference, so this is the image of the cat and this is a generated image of the cat by this autoencoder. So one question is, how does it learn to regenerate that data or regenerate the image of a cat? Another thing is, why do we want to regenerate? What do we achieve by doing this? So one thing is that how does it learn is, it will take the original image, let's say it is O, and the generated image. So one way is you can calculate the error between the original and the generated image. So then this is called as the reconstruction error. So this is a simplified way and can the exact formula, but then just to understand the original minus the generated one. So this is the reconstruction error. How much does the reconstructed image deviate from the actual image, the original image? This is the reconstruction error. So we will say that the autoencoder has learned uh, the data once the reconstruction error is very low. When the reconstruction error is very low, then the autoencoder is said to be said to have learned the data. Now this is when the reconstruction error is low, but what do we achieve by just reconstructing the image is that, so here we started with a 128 by 128 image, and then we have passed it to many convolutional pooling, all those layers. Finally, we reach a middle layer. This is called as a latent space or a bottleneck. Now, if you see the size of this latent space or bottleneck, it is 10. So, it has reduced from 128 to 128 to 10. Just for simplification, I have written as 10. But then again from this 10, it will regenerate 128 by 128. So then this means that you have a very high dimensional data, you reduce it to 10, such that this 10 point have all the relevant information to reconstruct this 128 by 128 image. So this 10 points will have all the necessary information. It will not contain any redundant information, but it will have the most important information. So here we are doing dimensionality reduction, but this latent space contains everything, or a latent space or a bottleneck contains everything that is needed to reconstruct the data. So this could be, for example, if because we talked about cat, this 10 points could mean something like this. So these are the 10 points, okay. These are some random values. So the first value might represent the eyes of a cat. The second value might represent the fur of a cat. The third value might represent the tail of a cat. So all this will tell something that is important for this image of a cat. So this is how an autoencoder works, where we give an input X to an autoencoder. It will generate a latent space or a bottleneck Z, and it will reconstruct X hat or X. So how does it reconstruct? By minimizing reconstruction loss by minimizing the reconstruction loss. So if X is the actual data and X tilde is the reconstructed data, then this is the mean square error. So this will give us the reconstruction error. So here if we see this latent space or the Z that we are having, these are just points. These there is no structure on the Z value. These are just some random values. And the difference of variational autoencoder is here in how the Z is modeled. So in variational autoencoder, the X is not just mapped to a point, a single point Z. It's not a single point that it is mapped to. Instead, the X is mapped to a distribution. That is, so if you see here, this is the bottleneck. So before I told this might represent I, this might represent this might represent tail, etc. But in variational autoencoder, how this would look is you will have all these 10 points, but then it will not be a point, it will be a distribution like this. It's not a point, but it is a distribution. Each of the, so I's will have a distribution, her will have a distribution, etc. So there is no mapping to a single point, but the input will be mapped to a distribution. So then the encoder, so this part where the input X is given and is reduced or represented as a latent space, this part is called as an encoder. And this part from where Z is mapped to X tilde, this is called as a decoder. This is the encoder and the decoder. Now, the encoder here will not map to a single point but a distribution. So the encoder will be Q of Z given X. That is X to Z to X tilde is the process. X tilde is the process. This is the encoder. This is what the encoder do and this is what the decoder do. So encoder will create an Z given some X. So this is the encoder. This will tell the probability Q of Z given X. So this we can model as N of Z given some mu of X sigma square of X. This we can model as a Gaussian distribution, outputting the parameters mu of X and the sigma square. So then this Z is our prior. So P of Z is, we can model this, we can assume that it is having a zero mean and unit variance. So this is an assumption. Prior is when we don't have any information, we assume. So N of, this is a normal, we assume that this is a normal distribution. Then the decoder will be P of X given Z. Now we want to maximize log of p of x, and this is given by log of p of x given z into p of z. So this is something that is not very tractable. Like computationally, it will not like it will not finish in a polynomial time, but it will take some complexity that is higher than polynomial time. So it is computationally intractable. So they have come up with uh, something called as evidence lower bound. That is elbow. So here they say log of p of x is greater than or equal to the expectation of q of z given x into p of x given z minus kl of q of z given x and p of z. So this is the elbow, this part. This part. I will tell what this means. So what we started with was latent space z. We don't know what this latent space is. So we assume that it is a Gaussian with zero mean and a unit variance. Now, we want to, so the encoder will give q of z given x. We want this q of z given x to match this prior. They should be similar. This is what the KL divergence measure. So KL divergence measure the similarity between probability distribution. So this is our encoded output, and this is our assumption about the latent space P of Z, the prior. So we want the encoded output to be to match as that of P of Z. Now why this is the case is, so here as I told before, for each of the points, we have a distribution. So this i's will have a distribution mu1, comma, sigma 1 square. This will have a distribution mu2, comma, sigma 2 square. This will have a distribution mu3, sigma 3 square, etc. So now this is together uh, is a multivariate distribution. That is, it is consisting of multiple parameters. That is, mu1, mu2, etc. up to mu10, and sigma 1 square, sigma 2 square, etc. up to sigma 10 square. So, this is a multivariate distribution. So, when if you don't model it as a distribution, the issue is with the autoencoder, when you don't model it as a distribution, this will be just some random samples in the data. But when you model it as a distribution, each of this, maybe each of this might belong to some distribution like this. But together, when we when we add this scale divergence term, it will make one full cluster that will have all the possible distributions of the different points. So we want the prior to be similar to mm, the encoded output. That's why we are doing that part. Now the other part is the reconstruction error. That is the same, somewhat similar as the reconstruction error that we have discussed with MSE or the mean squared error. So, yeah, so this is what a variational autoencoder would do. Now, coming to GAN, in GAN, we have two networks. With this, we have a generator and a discriminator. So the generator will map. So you have the encoder, the bottleneck, that is the Z, and then the decoder. So the generator will map the Z to some random or a synthetic sample. Then what the discriminator will do is it will take this sample, and then output the probability that it is real, whether it is a synthetic, whether it is actual data or it is a synthetic data. So this is what GAN would do, where there are two networks, generator and discriminator. Now, for the GAN, if suppose if there is X for the discriminator part, if there is X, then it is given to the discriminator B of X, it will output a value between 0 and 1. So that is the probability. 1 is when there is real data. 1 is when the probability is high, that is that it is real. And 0 is it is the generated data. Okay. Now, I think I'll discuss some questions. In the GAN network, what are the two neural networks involved? Encoder and decoder, teacher and student, generator and discriminator, classifier and regressor. Yeah. So in GAN, there is a generator and a discriminator. A generator is used to generate data, and the discriminator will distinguish between the real and the synthetic data. What is the input to the generator network in GAN? Training data, random noise vector, output from the discriminator, encoder representation of the data. Yeah, so it is the random noise vector. So in the GAN architecture, the generator will take some random noise vector, and then this random noise vector is sampled to uh, synthetic data sample, and then during training also the GAN never see the actual training data directly, but then it will learn to map the random noise to the data distribution based on the feedback it receives from the discriminator. So the discriminator will take either real training data or the sample from the synthetic output and attempt to distinguish them. Yeah. So then random noise vector means it could be anything. So uh, it can be from standard normal distribution or any other distribution. So it is not an actual data. It is just some noise that you are giving as input, any distribution data. What is the bottleneck layer in an autoencoder? The layer with the largest number of neurons, the layer where dimensionality reduction occurs, the layer with the slowest computation time, the final output layer. Yeah, so autoencoder, the bottleneck is where the dimensionality reduction occurs. So it is between encoder and the decoder. And with the encoding process, it will reduce the dimension of the data to this bottleneck layer. So it will have a compressed representation of the input data. What is the key advantage of using variational autoencoder over traditional autoencoder? Variational autoencoders are computationally less expensive. They provide more structured and meaningful data representation. They automatically classify the input data. They require less training data. So the variational autoencoder, it will learn the probability distribution um, of the latent space. So the benefit with variational autoencoder is that when you have in the input text, when you have similar data point, they all will get mapped to nearby points. So this will result in a very structured and meaningful latent representation than uh, the normal autoencoder, which will just compress the data to some fixed size latent space. So one benefit with this is that it will also allow to generate new samples. So once we know that in the latent space we have distribution instead of fixed point, so we can also generate data from that. That is another advantage. So here it provides more structured and meaningful latent representation. An autoencoder has layers 784, 512, 128, 32, 128, 512, 784. Which layer is the bottom? Yeah, so it is the middle one, 32 neuron base. So in a convolutional autoencoder for images, what operation is used in the decoder to increase the spatial resolution? Fully connected layers, upsampling layers, max scaling, threaded convolution, the downsampling picture. Yeah, so you have to upsample the layers to increase the spatial resolution. So in the decoder, you have to increase the size. So you have to upsample rather than downsample. Uh, to pass the exam, you can check the discussion forum, not the discussion forum, the announcement page. I think in the beginning they have mentioned the distribution of uh, assignment questions. because all those assignment questions are also important for exam. Some part of the questions for the final exam might come from the assignment question. So we can see the distribution there. I don't exactly remember what was the distribution, but we can check that uh, to know. I think there they have mentioned the passing criteria. So in a standard GAN, what is the primary objective of distributor? Sorry, discriminator. Yeah, so it is a binary classifier that distinguishes between the real data and the generated data. So the as we mentioned before, there is a generator and a discriminator. The generator will take some random noise vector result and then it will transform that into a synthetic data sample. And so the main goal of the generator is to produce some output that is indistinguishable from the real training data. So this is the main goal of generator. And the discriminator, as we told, want to find whether it is a real image or it is a fake image. So the goal of discriminator is to correctly identify real samples and fake samples. So both the generator and the discriminator, they both are trained simultaneously. The generator will try to fool the discriminator, but the discriminator will try to correctly classify. So there is always a competition between the discriminator and the generator. Then the objective of GEM, there is this long objective function. I will just quickly make it. Have to use. Now, what this means is uh, so this the first term is the expected. This is the expected log probability. So this is the expected log probability that the discriminator correctly classifies real data as real. D of x is the discriminator. So this is the expected log probability. It will tell the probability that the discriminator correctly classify the real data as real. So when we maximize this, this will uh, this will lead to the p of x going to or moving towards 1 for real samples. Now the second term, that is p of log 1 minus t of g of z. This is the expected log probability that the discriminator correctly identified fake samples as fake. That is when 1 minus d of g of z, when it goes to 1, then this. So when this is maximized, then the discriminator is actually correct. So this part, this first term and the second term together, the discriminator maximizes these two to be a better classifier. Now, the generator, what it will do is it will minimizes this first and the second term. So, discriminator will maximize and the generator will minimize, especially the second term, because the first has no generator parameters. It is only the log of d of x. But here, uh, there is generator parameter. So it will try to minimize this parameter, the discriminator's ability to detect fake sample. That is what the generator will try to minimize. So there is always this competition between this discriminator and the uh, generator. So that is the main objective, the min-max objective function. So one is trying to maximize and the other is trying to minimize. This competition happens between generator and the discriminator. So this is the min-max objective of GAN. So then, let's see. So in an autoencoder, when you have a continuous valued image input, what is the loss function that is used? So for continuous valued input, we always take the difference between the actual value and the reconstructed value. So mean squared error is a good function to do that. Uh, the VAE encoder outputs mu and log of sigma square for each input. What probabilistic quantity do these parameterize? The joint distribution P of x comma z of inputs and latent thought. The Tire distribution P of z. The approximate posterior Q of z given x. Q of x overall possible values. So it is the approximate posterior Q of z given x. Now, when we consider GAN, there is this latent space in the GAN. So in GAN, the latent space is the space from which the input noise vector is drawn. It is the input domain of the generator G, and it can be any distribution like normal distribution or uniform. The generator will map each point in this latent space to a corresponding image in the data space. So different points in the latent space will correspond to different generated images. And so the generator will learn some transformation, and that will determine the structure of this latent space. Now, once the training is complete, generating a new image is simply a matter of sampling a random method and passing it through the generator. So, uh, so importantly, the mapping, when we consider it is continuous, so nearby points in it will produce similar looking images. So that is this. That is what the latent space in GAN would refer to. So compared to convolutional GAN, there is this deep convolutional GAN, which is the DC GAN. So it will what is its difference is it will replace all the pooling layer with strided convolutions in the discriminator and transposed convolution in the generator. So why is it useful is it will allow the network then to learn its own spatial downsampling, upsampling, and it will remove the information bottleneck of max pooling. So another difference in architecture for DC GAN compared to a GAN is they use batch normalization in both this discriminator as well as the generator, and also they remove the fully connected hidden layer. They uses only convolutional layer, and they use ReLU activation in the generator and DP ReLU in the discriminator. So these are the differences in the architecture between GAN and the DC GAN. So as shown in the video, when we consider DC GAN, it starts with a 100-dimensional noise vector, which is sampled from a normal distribution of 0, mean, and 1 variance, unit variance. So they first reshape it into a tensor of size 1024 by 4 by 4. That is 1024 features of spatial size 4 by 4. Then they uses a series of transposed convolution layer And then progressively, they increase the spatial resolution while decreasing the number of feature maps. So I'm just describing the architecture of PC GAN. It's just, there's not a lot of things to explain. So then they uses 512 by 8 by 8, and then in the next layer it is 256 by 16 by 16, and then in the next layer 128 by 32 by 32, and finally 3 by 64 by 64. So each transposed convolution layer, it will double the spatial dimension and half the number of channels. And batch normalization and ReLU was one difference from GAN that was used in DC GAN, and that is applied after each layer except the last, which uses the TANH activation. And finally, there is an output which will have a free channel 64 by 64 RGB image. So this is what happens in a DC GAN. So this activation function is used at the generator output in DC GAN, and which is used in the other generator layers. Sigmoid at the output, ReLU in all hidden layers. PT ReLU at the output, sigmoid in all hidden layers. TANH at the output, ReLU in all hidden layers. Softmax at the output, TANH in all hidden layers. Yeah, so it is TANH at the output, ReLU in all the hidden layers. So in a DC GAN generator, the 100-dimensional noise vector Z is first projected to watt shape before the transposed convolutional layer. A flat 1D vector of 4096 elements passed directly to a fully connected layer. A 1024 by 4 by 4 feature map tensor then progressively upsampled to 3 by 64 by 64. A 3 by 64 by 54 tensor then downsampled to 1024 by 4 by 4. A 512 8 by 8 tensor upsampled to 3 by 64 by 64. A 1024 by 4 by 4 feature map tensor. To train VAE is used for data generation. Which of the following correctly describes the generation procedure? Pass a training image X through the encoder, take mu as Z, decode to get X tilde, sample Z from Q of Z given X for a randomly chosen training image X in decode, sample Z from the prior, pass Z through the decoder to get a new sample, average all the training latent codes and decode the average to generate the sample. So the question is about generating new sample. It's not about uh, reconstructing sample. So the first, the A option deals with reconstruction. So it is X and X tilde. X tilde is the reconstructed output. That is not what is asked. So what is asked is the generation procedure. How is the generation procedure done? That is by C. That is you take a sample Z from the prior P of Z and then pass it through the decoder to get a new sample. So the prior distribution is learned to generate new sample. So there is a deep neural network. So this is a classification network. And this classification network is trained to diagnose pneumonia versus normal chest X-ray. So the input is an image, which is a chest X-ray image, and the label is either the X-ray shows pneumonia or the X-ray is normal. So there's a classification network. So what kind of distribution will this classification network model? Is it P of X, the distribution of the chest X-ray, the input, or is it the joint distribution of images and diagnosis, or is it the posterior probability of diagnosis given the image, or is it the distribution of image given the diagnosis? So this is a discriminative model. So in a discriminative model, what is model? So in a discriminative model, P of Y given X is model. That is the posterior probability of the diagnosis given the image. Whereas in a generative model, we learn the joint distribution of the images and the input and the output. So here it is a classification network and it is a discriminative model. So given some input image X, it will output P of Y given X. That is the probability of each diagnosis. It does not model P of X and it cannot generate or synthesis new image. It's just a discriminative. Thank you all for attending today's session.